Section 8 is on nomenclature, or how to name things. In this video, we're going to talk about naming ions, some of which you know how to do. For a quick review, let's start with a sodium atom. Sodium atom has 11 protons and 11 electrons, and we see that there's 1 electron in its valence shell. Now you can say gain 7 or lose 1 to get to the octet. And for sodium, it's easier to lose 1 electron. So you now have 11 protons and 10 electrons, and there you have the octet. For the ionic charge, you take the number of protons, and then you add the electron, the negative 10 charge, and you end up with plus 1. So you would say you have sodium 1 plus, or the sodium ion, and because it is positively charged, it is a cation. In another example, we take chlorine, 17 protons, 17 electrons, 7 electrons in the valence shell, gain 1 or lose 7. 1 is obviously smaller. So chlorine will gain 1 electron. It now has 17 protons and 18 electrons. 17 plus 18 negatives is minus 1. So we would have the chloride ion, Cl1 minus. And because this is negatively charged, this is an anion. For the representative metals, except for tin and lead, but including zinc, silver, and cadmium, in order to name the ion, all you have to do is name the metal and add the word ion. So for example, we have the sodium ion. For the transition metals, except for zinc, silver, and cadmium, but including tin and lead. Now you need to name the metal, then use the Roman numeral, which tells you what the ionic charge is, and then the word ion. So for example, with chromium, you would have chromium 2 or chromium 3, depending upon the conditions, and you do need to know which one you have. And in a later lecture, this will become more evident. For the representative nonmetals, which is sort of redundant since all of the nonmetals are in the representative section, and really only looking at these representative nonmetals, you need to change the end of the element to IDE, and that takes care of it. So for example, if you look at chlorine, when it becomes an ion, becomes chloride. So now it's on to a new topic. Chemistry would be really boring if all you could do is combine simple elements as positives and negatives, and so we're going to have to deal with polyatomic ions. We've been dealing with monoatomic ions. Mono means one, and you guys have all seen in some way, shape, or form a monorail, a train that runs on one rail. Monoatomic ions have one atom in the ion. For example, the sodium ion, the cobalt-3 ion, the selenide ion, all of which are just single elements. Poly means many. Polyatomic, many atoms. Polyatomic ion, an ion made up of many atoms. Here, many means 2 or more. So for example, oxygen can be bound to hydrogen, and this would have a 1 minus charge. This would be written as OH1 minus, and this is the hydroxide ion. Here you have 3 oxygens and 1 phosphorus. We would write this as PO3 minus, and this is the phosphite ion. When you look at a polyatomic ion, you need to pretend that the atoms of that polyatomic ion are superglued together. They will not break off. For example, the 3 oxygens attached to the phosphorus here are not going to split away from the phosphorus when this is put in water, and this is a polyatomic ion with a 3 minus charge. There are lots of polyatomic anions. There's only one polyatomic cation, and that is NH4 1+, which is called ammonium. And yes, you will need to memorize this one. How do you know you have a polyatomic anion? Most of them end in ate or ite. For example, sulfate, which is SO4 2 minus, nitrate, NO3 1 minus, nitrite, NO2 1 minus, oxalate, C2O4 2 minus, hydrogen carbonate, HCO3 1 minus. You do have 3 that end in IDE, hydroxide, which is OH minus, cyanide, which is CN1 minus, and peroxide, which is O2, 2 minus. How do you know what to call a polyatomic anion? You just have to learn them. But you're not going to have to memorize them. You're going to be given a sheet with many of the more common polyatomic ions given. Now you just need to remember to look at the sheet. It's important to realize there is no relationship between the 8 or the ite and the number of oxygens. But the ites have one less oxygen than the 8s, but the ionic charge stays the same. So for example, sulfate, SO4 2 minus, sulfite, SO3 2 minus, chlorate, CO3 1 minus, chlorite, ClO2 1 minus, phosphate, PO4 3 minus, phosphite, PO3 3 minus. And if you noticed in those three examples, for the 8s, there was no relationship to the number of oxygen and the fact that it was called, for example, phosphate. That's how you name polyatomic ions. For the most part, you look at the sheet, but you need to know to look at the sheet. So to review, metals will always be cations, positively charged. For the representative metals, just the name of the metal and the ion. For the transition metals, you need the name of the metal, the Roman numeral for the ionic charge, and ion. Nonmetals, when bonding ionically, which hints at the fact that sometimes they don't bond ionically, will always be anions or negatively charged. You're going to take the root of the nonmetal, and IDE, and polyatomic ions have more than one atom in the ion. Those atoms of the polyatomic ion are superglued together to make one gigantic ion. There is only one polyatomic cation, and that's ammonium. Write that down. Polyatomic anions, most but not all, end in either ATE or ITE. ITE always has one less oxygen than the ATE. 3 will end in IDE, hydroxide, cyanide, and peroxide, and you just have to learn them. So that ends our review of naming ions, including a slightly new section on the polyatomics. In the next sections, we're going to learn how to name specific chemicals using generalized rules, but really just a subset of chemicals out there.